Now let's apply principle of virtual work to an axial bar. And let me discuss what axial bars are first so you have a better understanding of that. But before I continue with that, I want to remind you what we did in the previous lecture. So for 3D theory, we, we're going to use something called the principle of virtual work. The principle of virtual work states that for every body, every structural body under loading conditions, that body will be in equilibrium if the external virtual work equals the internal virtual work. And I can calculate external virtual work and internal virtual work very simply. Once I calculate strains for that theory, in this theory there are 6 strains, and these strains are then plugged in into the virtual work principle. Once I do that, I will integrate by parts to remove any derivatives. Here I had the comma j. And then once I do that, I integrate by parts. I basically put all the terms together, and I use the fundamental lemma of calculus variations to get the equilibrium equations of elasticity, which is a very powerful idea. Notice how I never brought in here the constitutive relationships. Notice how the equilibrium equations, the Cauchy's relationships, and the deflections came out, but there's nothing here about constitutive law. That's okay. The constitutive law, that means that this theory works for large deformations and large, and also is not, it could be large deformations, but also material, the material can be nonlinear as well. So there's no assumptions made here whatsoever. This is a very general statement. And we're making really good progress on how to derive theories now. So let's look at how we will go about deriving the bar theory. So a bar usually, so bar theory. So I'm going to apply, this is my first application other than 3D theory. So this is application two. So you can see how that works. So bar theory, bars typically, like a rod, does not bend. So this does not bend. So that's the first assumption. And bars can only stretch or compress. Okay, so that's an assumption. You can found these systems in trusses or struts. So let's consider then, for this particular example, and I'm sorry, I'm going to erase this to draw a more general cross section because it can be a general cross section, and that's not a very good cross section, so I apologize. So big cross section like that. And let's say it has a uniform distributed load Q. That's okay. You can do that. So there's tractions applied on the outer surface. Let's apply traction surface, traction loads on the outer surface, all around the circumference. Okay. And then say I have a load, and then these coordinates x1, and the length, let's call it L. Let's call it L. So the deflection, the displacement assumption, you have to first then look at the displacement assumptions. The displacement assumptions for this theory, if it doesn't bend, if this bar cannot bend, just stretch and compress. It does not bend. So state the assumptions first. So that's step number one. And typically they'll be provided. Unless you're getting your own PhD thesis, then you have to then come up with those assumptions yourself. But the assumptions for this theory are typically going to be given to you. And I'll give them to you as we move along for the various theories. So assumptions for this theory is that this bar can only stretch or compress. That's it. It cannot do anything else. So that's used in trusses. That's where it can be used. Examples are trusses, and so trusses and struts as an example. Step number two, what we want to do is come up with displacement field assumptions that is consistent with these assumptions. So if I look at the theory very carefully, you can find that U1, for this theory to work out, U1, and I'll make a big U1, is x1, x2, x3, a function of, so the deflection in this direction is U1, say. I'm going to say it only depends on x1, has to be, because there's no bending, it's not going out of plane. So it has to be that the deflections at any point on this body, any point, that's why I have x1, x2, x3, that the deflection u1 at any point of the body, what we're saying is that the deflection in the axial direction only depends on x1, is independent of x2 and x3, meaning the deflection here u1, the deflection u1 here, the deflection u1 here, the deflection u1 here, those are all equal. So it does not depend on where you are through that cross section. Okay, it doesn't matter where you're in that cross section, u1 is the same. So therefore this has to be true, and that's what is called one-dimensional theory, is because it only depends on one coordinate x1. The other assumption made in this theory is that u2 is 0 and u3 is 0. So now your next step is to calculate all the strains. So calculate strain for this theory. So in this theory, I know what the strains are, and I'm going to use the infinitesimal strains. I could use the undeformed body strains, Green Lagrange, but I'm going to just go with infinitesimal strains as it applies for many different problems. So we know that epsilon ij equals 1/2 ui comma j plus uj comma I. I challenge you right now, and you will see that epsilon 1, for example, is derivative of u1 respect to x1. And that's just simply derivative of small u1 x1. And for making it simpler, I'll just call it u1 prime. It just makes it simpler. But if you continue, you'll find that epsilon 2 is 0. You'll find epsilon 3 is 0. You'll find that all the other strains are 0. So even the shear strains are 0. So in this theory, you'll find shear strains epsilon 1, 2, epsilon 1, 3, epsilon 2, 3 are 0. If you make these assumptions for this theory. Very good. We make good progress. So that's how you'll go about that. And so now step number 4 in this theory, step number 4 is to invoke the principle of virtual work. And I applied tractions here as an example, like on the lateral surface, but there's many other ways you could apply that traction. There's not only one way to do it, there's many other ways to do it. So if I apply the principle of virtual work, it states the internal virtual work equals the external virtual work. And internal virtual work is a triple integral over the volume, sigma ij, del epsilon ij dv. And the good news is, and let me just write the other terms, triple integral, body forces del ui dv plus the double integral over this surface, the lateral surface. Let me call it SL, the lateral surface. Ti del ui ds. Okay, so that's that surface. And so next, and then I can also add the inertial forces if I wanted to. So minus triple integral rho, and then I have ui double dot del ui d volume. I want you to notice how in this example problem where I'm deriving this theory, there's no gravity. In this example, I did not apply gravity. So in this example, no gravity, but in the future, I could apply gravity if I wanted to. So this is 0 because there's no gravity in this problem. No gravity in this problem. In this problem, I only have one deflection that matters because the other ones are zero. This is zero, this is zero. So as a consequence, I'm left with triple integral for this term, triple integral of rho u1 double dot del u1 dv. But note that u1 does not depend on, only depends on x1. In fact, let me write it out so it can be kept in your mind. Let me remind you why, because we said that here. That was an assumption of this theory. So as a consequence, none of this depends on, none of that depends on the cross-sectional area, x2 and x3. And I can actually, in fact, write it like this, dA dx1. It does depend on dx1. So this whole term then can be written as the integral, okay? This whole thing can be written as the integral from 0 to L. And since it does not depend on x2 and x3, then all this can go outside the integral. So I get rho A, right? Rho A, u1 double dot, okay, x1 del u1 dx1. So that's what I get for that one. So and I'm gonna collapse this better, no gravity in this example problem. This term, clearly this term, can also be looked at very carefully, and that's triple integral of sigma 1 del epsilon 1. Why is that? Because epsilon 2, epsilon 3, epsilon 1, 2, epsilon 1, 3, epsilon 2, 3, those are zero. You can see that from here. This is zero, this is zero, these are all zero. The only term that survives is that epsilon 1 equals u1 prime, which depends on x1 alone, remember, because I said that here, and that's an assumption, a basic assumption of this theory. So clearly that has to be zero. And so as a consequence, I'm going to go ahead and substitute for this triple integral sigma 1 del u1 prime dv. And notice how u1 prime depends on x1 alone. Okay? So that's what we got. And the next thing I want to do is to convert this to dA dx1. Okay? And the next thing I want to do is work this term out. I want to work this term out. Let's look at this ds. The tractions are applied on the surface now. So let me just translate it here so you can see it. The tractions, and this is x1. The tractions are applied this way on the surface. So if I take this differential element here, this length is dx1. This length here is the circumferential direction, ds. Let's just call it ds. That's okay. The fact of the matter is that these tractions are applied on the perimeter. Okay, so I can then take that integral, and you will notice how then I have ti, and I have ti over that integral. So, and the only term that really exists is del u1. So it's really tu1, t1, which is a traction applied in that direction. So t1 del u1, okay? And to keep it simple, why we don't call this perimeter a circle? So that the integral is much easier to calculate. Just for as an example. So switch to a circle as an integral. Cross-sectional area is a circle. Cross-sectional area is a circle. And we're going to do that to simplify it more. So then I have this integral. So this ds is really dx1. And then the circumferential direction is ds. And let's presume that the traction is constant around the circumference, but it can vary in the x direction. So in other words, this traction Q only varies in the x1 direction, but not around the circumference. It's constant around the circumference, which is totally good assumption. So I have T1, 2 pi r, the radius of the circle. So that's correct. And then I have dx1 from 0 to L. And then, sorry, and I have del U1. So I'm applying, and I can call this whole thing Q, force per unit length. So that's what I get for that term, the tractions. I'm applying traction forces on that surface. I only have T1 times del U1. And then I notice here that if I integrate around the circumference for a circle is 2 pi r. So T1 times 2 pi r, if the radius of the circle is r, of course, then I can call the whole thing Qx1, and that's known because that's provided in the problem statement. So let me now write it in one step, like what it looks like, because now things look a little more messier. So we'll just simplify it nicely. Triple integral sigma 1 1 del u1 prime x1 dA dx1 equals integral 0 to L t, and then I just called the whole thing qx1 del u1 dx1 minus integral 0 to L rho a u double dot 1 x1 del u1 dx1. Beautifully done. Beautifully done. And now I want to look at this term carefully. So this term I want to look at carefully, and I want you to notice that this does not depend on dA. So I'll bring it over here on purpose. So then I have triple integral sigma 1 1 dA del u1 prime x1 dx 1 and blah blah blah. I'll leave the right hand side empty for now. I don't want to have to deal with that term right now. What I want you to notice is that if I switch the order of the integral, and I have this dA, so these two integrals are for the single a, while this one goes from 0 to L. What I'm going to do with the left hand side, I want you to notice that sigma 1 1 dA has a physical meaning. If dA represents a differential element in the cross-sectional area, because that's what that is. This is a differential line element along the length of the rod. If I look at the cross-section and I look at a differential line element dA, which is dx2 times dx3, and I integrate it over the area, sigma 1 1 integrated over that area dA, delta dA, differential element, isn't this a internal force quantity n? So I can call it n, and I will do that now. So I'm going to call this whole thing n, or an internal force quantity. That's an internal force quantity. So then I get 0 to L n del u1 prime x1 dx1 equals to everything on the right hand side, which I will not repeat. So very powerful, because isn't this n representing the internal axial force in a bar due to loads applied externally? That's exactly what that is. So in 3D theory, the reaction forces of inside the body, when I look at a cube, are given by the stresses, sigma 1 1, sigma 2 2, sigma 3 3, sigma 1 2, sigma 1 3, sigma 2 3. But in an axial bar, the internal force reacting the external forces is given by n, because sigma 1 1 is a stress. And you can see that here. Let me draw this a little bit better so you can see that. So if I look, if this x1, sigma 1 1 is that way, because that's what sigma 1 1 is. Phase 1 in the one direction is acting on a volume, on a surface element dA, So that's definitely a forced quantity n. So now I can write that in the completely on the next page as follows. The integral from 0 to L qx del u1 dx1 and then minus 0 to L rho u1 del u1 dx1, and then I'll bring everything to the other side of the equation. So this is equal to 0, integral 0 to L n del u1 prime dx1. So that I just transfer everything to the other side of the equation, these terms here. And so now the next step is to integrate by parts. So that's integral parts. So that's n del u1 prime, pass the prime over. So I get this plus minus, but because this is a curve, is a one-dimensional problem, the integral one-dimensional problem is just endpoints. That's why there's no n here. There's no n there. There's no surface normal for that. So then I have 6. So when I integrate parts, I just continue 0 to L. And then this goes back into the integral minus n prime. And notice how these del u1s factor out everywhere. So I'll just do it in one shot. And then I have the boundary terms, which is n del u1 x equals 0, x equals L, because the boundaries of this bar go from 0 to L. And now I invoke the fundamental lemma of calculus variations, and for any del u1, I get the equation. Notice how this was plus, because I brought this to the other side of the equation. So that was a mistake. So then, by the fundamental lemma of calculus variations, what's inside the integral factoring del u1 is minus m prime minus qx1 plus rho u1 double dot equals 0 between 0, x1, and L. And then I have the boundary terms, which is either at x equals 0, either n is 0, so no axial load is applied on that surface. So if this is a bar, and this x equals 0, and this is L, either no forces are applied, either you apply a force here or you don't. But in this case, I don't have an axial force applied, so it's n equals 0, or u1 is specified. Because if u1 is specified, then del u1 is 0. You cannot write del u1 is 0 here. Del u1 equals 0 is not complete if you did that. At x equals L, either n equals 0 in this case, or u1 is specified. And I have just derived bar theory, and this is going to match very closely to what you learn in school in mechanics and materials. You've seen this before, in other words. I can now use the constitutive relationships to figure out what this equation looks like. It's just in terms of deflections, since that will be very convenient to know. So in terms of deflections alone, step 7, I have nx equals, nx1 equals double integral, not triple integral, of a over, sorry about that, of the cross-sectional area A, sigma 1 dA. And for one-dimensional bar, clearly, I get E times epsilon 1 dA. And notice how epsilon 1 is U1 prime. but dA is dx2 and dx3. So this does not depend on the cross-sectional area. So therefore, I just get EA U1 prime X. So I know now what N is in terms of EA of deflections. So I can plug it back in here. So I get that the equilibrium equation in terms of just deflections is minus EA U1 prime of X prime minus Q of X plus rho A U1 double dot equals 0. And this is the equation, the differential equation that can be solved for U1. And here U1, I was not talking about time, but U1 does depend on X and time. I just didn't go into that particular, I didn't write time here. Okay, so that's how that works. And I'll be then covering. So this is how you'll solve that problem, right? You have the differential equation, you have the boundary conditions that come from here, and you're set to go. From there, you're set to go to then continue forward with the derivations. So that resumes the calculation for today's lecture. I'll continue next with the Euler-Bernoulli beam theory, and then I'll have you then proceed with Timoshenko beam theory.